Hello everyone. This video we're going to use Jamovi in order to help us do a one-way Anova test. So let's look at our scenario. So here it says that Blake is working at a convenience store. He's trying to determine if positive or negative magazines at the cash register actually promote more sales. He decides to test three scenarios: one register with no magazines, one with positive magazines, and one with negative gossip magazines. He randomly selects transactions at each tested register for a day. Blake wants to see which option performs the best for his clientele at the 0.05 significance level. Okay, so let's get our data into Jamovi to get started. Let's go ahead and click on data. Let's copy it and let's bring it on over. Paste it in. Go ahead and relabel this. So our first one is just going to be magazines. And our second one is just going to be dollars. The dollars came in as like continuous and decimals. So that's great. And then our magazines looks like it's nominal in text, and that actually looks really good. We are going to change just the order that these are put in, not because that there is an order, but this is the order at which the problem is actually doing the analysis. You could make a claim that maybe this is ordinal by putting like positive as 1, no magazines as 2, and then negative as 3, if you kind of did like on some sort of little Likert scale. But we're just going to put this in the order that the problem is doing them in, which is signified by the group 1, group 2, and group. Okay, so let's go ahead and hide that. And let's go ahead and look at our questions. So what type of data are we dealing with? Well, since we're dealing with an Anova, we're dealing with this, what's numerical by categorical. And we actually were kind of doing this with our two-sample hypothesis testing of the means in our previous week. And so this is really, we are interested in the true mean amount spent in dollars, and we're breaking it up between, instead of just two groups as we were doing previously, but now we are doing 3 groups or 4 groups. We can handle lots and lots of groups now. That's what Anova is good at. So the grouping variable of interest that we have here is our magazine status. Is there no magazines? Are there positive magazines? Are there negative magazines? That's our grouping variable, or the groups that we are comparing to one another. So the response variable then is just how much was spent when a transaction was made at one of these different groups. So a population that is not of interest, if we kind of look at here, we are interested in registers with negative magazines, with the no magazines, and with the positive magazines. This one, we could have done this if we had both positive and negative magazines at a register, but because we didn't do that in this test, that's actually the one that we are not interested in. So the parameter of interest is the true mean amount spent with respect to each of these groups. We're comparing the true mean amount spent between each of them, and we want to see, it's like 20 of these groups have a true higher mean than, or lower mean, I guess, than any of these others. Okay, so one of these other kind of preliminary questions that we have is, can the variances be considered equal? And in order to do this, what we are going to look at is we're going to see if the standard deviations are within 2 times of each other. We did this previously as well when we were checking our variances with our 2-sample test, and we can do this with our Anova testing as well. So let's go ahead and dive into our analyses. Let's go to our analyses and let's do just a basic data exploration, and we're going to just grab a descriptives. And we're going to make our variable of interest be our dollars, and we're going to split by our grouping variable is going to be our magazines. And then instead of doing across columns, I'm going to do across rows. I'm going to get rid of a bunch of these statistics just so that I can have some of the basics. And let's take a look at what we have. So in these descriptives, we are given our sample size of each of the groups. They're pretty close to one another, maybe a little small here. We have the means with the 48 for no magazines, 44 for positive, and 50 for negative magazines. We have our standard deviations, and what we need to check if we are looking at seeing if we have close enough variances for homogeneity of variances, or like equal variances, is we want to do just a quick check to see if our standard deviations are within 2 times of 1. So we can do this real quick inside of R. Let's go grab our RJ editor real quick. I'm going to go and type options digits equals like 7 or 8 right now, and just give us enough decimal places so that it looks good. And then I'm just going to do a very simple, I'm going to call this like var check. You can label this whatever you want. It's just a kind of placeholder. And I'm going to do this 7.25926, or instead of var check, let's call this a standard deviation. Okay, and then we are going to divide that by our smallest standard deviation. Smallest standard deviation is with 2. And you might say, well, how do you know which one's the biggest, which one's the smallest? You literally look at the number. Which one is the biggest standard deviation? Which one is the smallest standard? All right, so our smallest one is 5.08213. And then right below this, so I can actually see what the value is, I'm just going to type out SD check. Make sure that it's exactly the same with the same capitalization and everything. And let's go ahead and run this guy. So I'm just going to hit run. Oh, and then I like to also push this gear, and I like to say show code and output so I can see kind of what's going on. And it says that this check between these two gives me 1.4. So this is less than our kind of cutoff of 2. So we can consider them to have equal variances. Okay, so let's go ahead now and let's go back to some of our questions. So can the variances be considered equal? We say yes, the variances can be considered equal. All right, so which equation should we be using for our test statistic? Let's go ahead and look at all of these. So these are kind of the different methods that we have. And what we're going to be using here is Anova, because Anova lets us compare more than one groups to one another. Okay, so then which distribution should we be using? In Anova, we're actually going to use a new distribution that we haven't used before. So previously we've been using like the Z, T, and the chi-squared. And now we're going to be using our F statistic. Okay, so one of the other checks that we have to do with Anova is we have to see, it's like, do we have normality? So there's a couple ways that we can check for normality. We can look at the histograms of each of the groups and say, it's like, hey, do we have normality? So we have our data coming in here, and we can actually just look at it in here from MyOpenMath. Let's kind of take a dive in real quick. Let's go back and look at we can go back to our descriptives, and we can come down onto our plots. And there's some things that we can grab. Let's go ahead and grab a histogram plot. So this is the different groups put together. And what we're looking for, it's like, do each of these groups generally have a normal distribution? And it has to be like really bad before we start freaking out or having problems with it. So this one looks basically normal. The second one looks pretty normal. It's not too bad. This one, maybe we've got some problems with. So that's one way. But there's another way that we can look at this as well. And we can look at what is called a QQ plot. And we can actually grab it right here. We can grab this QQ plot. And so this is looking at like QQ by the groups individually, or we can look at them all together. So this is one way that we can look at the QQs. And essentially, it's kind of shorthand. Normality means that these dots are going to be landing pretty closely to the line. Now, is it perfect? And the answer is like, no, it's not perfect. But do they generally follow this straight line? And we're like, yeah, generally they follow the straight line. So we can check out all of those. Now, the other way that we can do this is that if we don't look at it, let's actually grab a new one. Let's go to analysis, exploration. Let's do a new descriptive. So instead of looking at it by groups, we can look at let's get rid of all this stuff because we can look at the QQ plot as just an individual group, where these are all of our data points following a line. We can look at the QQ in just a single plot. And that's what happens in our MyOpenMath, where this is our data, and we just recreated this QQ plot. So it's like, do all of the groups look approximately normal? And the answer is, yeah, they look approximately normal. It's not perfect, but they look approximately normal. And same thing, does the QQ look like a straight line? And approximately, it looks like a straight line. So it looks like that we've met our requirements in order to actually perform our Anova test. Okay, so let's go ahead and now move on to establishing our hypothesis. So our null hypothesis says that the true mean amount spent at register for each group is the same. where this is basically saying that the mu for group 1 is equal to the mu of group 2, which is equal to the mu of group 3. Or we can say this again, that the true mean amount spent at registers without a magazine is equal to the true amount spent at registers with positive magazines is equal to the true amount spent with negative magazines. Okay, so that's what we're going to look for right there. And then when we look at our alternative, we have to be careful here. The alternative is not that they are all different. If they're all different, that's great. That would invalidate our null hypothesis. But what we are really looking at is that at least one group's true mean amount spent is different from another. That we have at least one pairwise comparison that is different. And we'll get into that a little bit more once we dive into our post hoc analysis with our confidence interval. Okay, now we need to identify our alpha, and we always look back up into the problem, and we see that we're testing at the alpha level of 0.05. So that gives us our alpha level, 0.05. And now we're looking at collecting data. So we're looking at x bar of 1, x bar of 2, and x bar of 3. We're looking at, okay, what the heck are the sample means? We actually already grabbed that. We can go back up to our descriptives, and we can see that the mean for group 1 is this 48.74. The mean for group 2 is this 44.3. And the mean for group 3 is this 51.929. Now we're looking for, okay, well, what's our F statistic and what's our p-value? Okay, at this point, we actually need to do our Anova analysis. We've gotten everything, but we haven't actually done our analysis. So when we do that, we can go up to our analyses, and we can go ahead and click on Anova, and we just want to go click on one-way Anova. From here, we're going to grab our dependent variable, or the variable that we're interested in. We're really interested in the amount spent, and we're grouping them by the magazines. Okay, so for this class, we are not going to, we are not going to run the Welches for not assuming equal variances. If we hit that point where we say that we're not going to assume equal variances in the Anova, we're just going to say stop. We shouldn't move on. But if you really did want to run an Anova without having equal variances, we can just click on here and use the Welches. But for us, we're just going to assume equal variances because we ran our test so that we could assume equal variances. And then we could do additional statistics. There's some cool stuff that we could hear. Instead of going through and doing the separately, like all of the Anova, like all of the descriptives, we could just say, hey, I want a descriptive table. It's like, hey, look at that. It gives me what I want. I could also run a descriptives plot and it gives this. It's like, okay, cool. Here's our kind of plotting the confidence intervals. That's nice. We could also look at our homogeneity test. These are some tests that you could actually look for instead of doing the check that we did, but we did the checks with the standard deviations. We could click on the QQ plot, and this reproduces yet again that QQ plot that we looked at before. And then let's go ahead and pause right there. There is one other thing in the descriptives that I want to look at. Let's go ahead and look at our descriptives. Another really good plot that we can look at is kind of these like box plots, because it shows us the distribution of these different groups, and we can kind of see it's like, okay, looks like positive might be a little smaller, maybe no magazines is bigger, maybe negative magazines is even bigger. So anyhow, that's kind of like some of the things that are going on there. Let's go ahead and go back down though to our Anova output. Back to our data. And here it asks you for your F. And it's just literally underneath here is our F statistic, this 15.5599, 15.5599. And we're given a p-value, and it's really, really small. So you could type like this is the actual p-value. Jamovi cuts you off at like 5 decimal places. It's just say, hey, you know what? It's really, really small, 0.00001. If you just put in this, it'll calculate it correctly, as you can just put in the 0.00001. Okay, so we now need to compare our p-value to our alpha. Remember, alpha was 0.05. P-value is this tiny number. So our p-value is less than alpha. Okay, so then we want to actually look at our confidence interval plot. If we want to attach that or anything, that is what this little guy is. So in order to attach it, you can just take a picture of it and paste it in. So that's our confidence interval plot. And our decision here is going to be rejecting the null because our p-value is less than our alpha level. All right, so in conclusion, okay, here we have that Blake collected sufficient evidence. And here's how you report our evidence. It's going to be F2-102. Let's go back up here and let's see where we get those from. So this is degrees of freedom 2. It winds up being the number of groups there are minus 1. And then we have our degrees of freedom here, and that has to deal with like our sample size. And anyways, it's a little bit less than our sample size. Regardless, this Anova table will just give it to you. Here's the 2, the 102, and then you provide your F statistic. Then you report your p-value, and you report your alpha level. All right, so we have Blake collected sufficient evidence to reject the claim that the true mean amount spent for registers with no magazines, positive magazines, and negative magazines are equivalent, and instead we conclude that at least one pairwise comparison is different. Okay, so now we know that there is a pairwise comparison that is different, but the next question should always be, it's like, well, which one is it? Which one do we think is actually different from the rest? Now, in order to do that, what we can do, let's go back here into our one-way ANOVA. And what we do is we want to do a post hoc test to determine, or like an after the fact test to determine, well, which ones do we think are actually different? In order to do that, we want to do what's called a Tukey test. It's called like a Tukey honestly significant difference. And we're just going to click all of these boxes on our statistics. Okay, so let's go ahead and go back, look here, and if we scroll down, we get this table. And in some respects, this table is handy, and in other respects, it doesn't give us quite enough. But what we can look at is we can say, okay, let's look at no magazines, and we're going to compare it to positive magazines. No magazines and positive magazines, there is a significant difference in here because it says that the p-value is less than 0.05. So it's like, okay, we see a difference between there. But between no magazines and negative magazines, our p-value is greater than alpha. So we didn't find significant differences. Finally, if we look at positive magazines and we compare it to negative magazines, we see that we have another significant result. The problem with this table, though, is that it doesn't tell you by how much. Like, I want a confidence interval. I want a confidence interval to tell me by how much are they different from one another. In order to do that, we need to write just a tiny bit of code, and it's very simple, and it's basically going to be the same every single time. So let's go ahead and go back to our analyses, and we're going to go look at the RJ editor. All right, so in here, what I'm going to type out is I'm just going to type out options digits equals, we'll do like 7 again. Then in here, I need 2 little lines of code in order to get me the Tukey post hoc confidence intervals. The first thing that I need to do is I'm just going to label this thing called my Anova test. And I'm just going to write this out. It's AOV, parenthesis, and then I need to put in the dependent variable. So for us, that is the dollars, or what we're actually interested in. Dollars. And then I need this little like tilde squiggly thing. It is the button next to the number 1 on your like number line on your keyboard. So you get, that's your squiggle, it's shift in that button. Dollars. And then what you can do is you can type in your grouping variable, which for us was magazines. Magazines. And then the last thing that you have to do is type data equals data. So the data that we put into our analysis right here is the data that we are calling on. Okay, so the only thing that would change if we were to do a different analysis so far is that these dollars and these magazines would change to whatever you have labeled your particular columns. Okay, let's go back to our analysis. Okay, and I'm going to, once again, to show output and code real quick. Now, the next thing that I need to do is I need to type out this line. So this is going to be Tukey. And you see how it pops up just like that after I started typing it out? You can finish typing it, or you can just click on it. Tukey HSD. And then what I need to type in is I need to type in Anova. And I do believe that that will give me what I am looking for. So let's go ahead and run this. And that's it. So the only thing that would change on a new round of this is that you would change your labels for the data for what you're interested in. So go ahead, write this down, have this in like your notes. I do not expect you to have this memorized, but we need this to give us a little bit of extra information. So let's go ahead and now look at what this Tukey test actually gave us. So here what we have is we have our magazines and we have the comparisons and we have the lower and the upper of our 95% family-wise confidence level. Okay, and then it has this extra level just because I guess there wasn't enough room to put this p-value right here. But these are the p-values that we saw in this table up here, like you can compare them. And we have significant ones where positive minus no magazines was significant. And we have negative minus positive magazines was significant as well. Now, there's a way that you can tell if they are significant or not straight from the tables. One is you could look at the p-values. We have less than 0.05 for the first one, greater than 0.05 for the second one, less than 0.05 for the third one. So that's a way that you can do it. The other way that you can tell is if you have two groups and you subtract them from one another, and the baseline assumption is that they're equal, if the lower and the upper are both negative, or if the lower and upper are both positive, that means that 0 is not in them, which means that they're probably not equal to one another, which means that you have significant. All right, so now that we have by how much we think, so for this one, let's interpret the first one. So we have positive magazines minus no magazines, and we have this as a negative value. So if it's negative, it means that we think that no is actually bigger than positive. And so I can actually say that I think that the true mean amount spent at registers with no magazines versus those with positive magazines was bigger by somewhere between, $8 somewhere between 78 cents to $8 more for the no magazines to the positive magazines. Now, if we look at the negative magazines to positive magazines, here we think that positive magazines actually sell better than negative magazines. We think that negative magazines sell better than positive magazines because this is a positive number. So negative magazines minus positive, since it's positive, we think that the negative magazines outsell the positive magazines on average by somewhere between like $4.36 to $10.89 on average. Okay, so now that we have that, let's go back and look at our MyOpen Math. So here we say that while conducting a Tukey post hoc analysis at the 95% confidence level, Blake found significant differences where two positive magazines has a significantly smaller true mean amount spent than both no magazines. This is the confidence interval that we found, and negative magazines. So that's how you go ahead and do your Tukey post hoc test. And that's how you wind up doing all of your stuff for Anova. So the nice thing is that Jamovi will handle just about everything. You need to do your checks right off the bat. And then once you do your checks, you put it into Anova. And once you get through, in order to get this confidence interval finished up, you do have to finish off with this little bit of code in order to get your Anova to finish up and give you how different you think they are. This code is very simple. If you have questions or you need help with it, feel free to reach out and contact me. Best of luck on running your Anova analyses on your own.